Okay, so for problem one, we're told that we have a spherical ball of ice with radius r that's melting in a uniform fashion, and we want to find a equation to describe the relationship between the rate of change of volume of the ice and the rate of change of the radius with respect to time for both of those. So what that means we're trying to find is dv dt, and we want to write it in terms of something in terms of dr dt. So what we first need is an equation to relate r and v. So we have a really nice equation for the volume of a sphere, which is v equals 4/3 pi r cubed. So taking the derivative of both sides with respect to t, well, the derivative of v with respect to t is going to be dv dt equals, this will be 4/3 pi, because that's all just a constant. Our r cubed, will apply the power rule, and we'll get 3r squared. But since we're taking the derivative with respect to t, we're going to have to chain a dr dt. And notice that this will simplify a little bit because this 3 and this 3 will cancel out and give us 4 pi r squared dr dt. And that's all equal to our big dv dt over here. So the correct answer for this one is, where'd it go? C, 4 pi r squared dr dt, and that matches exactly what we have. For part 2, we're told that f is a continuous and differentiable on the interval 1 to 6 inclusive. We also suppose that f of 1 equals -8, and f prime of x is less than or equal to 4 for all x in the interval 1 to 6. And we're asked, what is the largest possible value for f of 6? Well, we have some sort of a picture going on here where we know that f of 1, so here's our graph. So let's say right here is 1, is down here at -8. And then we know that we have a point at 6 that we care about. And since f prime of x is always less than or equal to 4, that tells us our slope is always less than or equal to 4. So if we want to find the largest possible value for f of 6, we're going to want to take the largest possible value for our slope. So that would mean we're going to set the slope to a constant 4. So we're going to say m equals 4. So we're going to go up at this with a rate of change of 4. So we can describe that behavior by this equation. We can take our starting point, or we'll think about this. We can take the equation y equals mx plus b. We know what our m is, right? That's going to be our 4. And our x, we know a starting point, and we know a y value, so that would be -8 is equal to 4 times 1 plus b, which we can then solve for b to get, this will become 4, so we'll subtract 4 from both sides, so b equals -12. Plugging that back in, we'll get y equals 4x minus 12. So if we want to find f of 6, what we're going to do is we're going to plug in 6 for x. So we get 24 minus 12, which equals 12. So the correct answer is E. For part 3, we are told to assume that g is twice differentiable on the closed interval 1 to 5 and has one critical point at x equals 2.5. We want to circle the statements that, if true, would be a valid justification that g of 2.5 is a maximum on this interval. So the first thing we can say is that if we want to have a maximum, it means we need to be at a critical point. And so if we are at a critical point, that means our derivative is equal to 0 or does not exist. So we know that this statement, g prime of 2.5 equals 0, needs to be true. But that's not enough. Just being a critical point is not enough to say that you're actually a maximum. To be a maximum, we would also need to be concave down, which means we would look like this, right? So our point up here would be our maximum. So that would mean that our second derivative is less than 0, which means we know that this isn't going to be true, and this isn't going to be true. Instead, we need this to be true. And because we know from the first one that I circled of g prime of 2.5 equals 0, we know that g prime of 2.5 is not less than 0, because that means it would still be decreasing. And if g prime of 2.5 was greater than 0, it means we'd still be increasing. So to cancel out the rest of these possibilities, I'm first going to talk about the last two, where we say g of 1 is less than g of 2.5, which is less than g of 5. Well, immediately we can tell that this is not true, because if g of 2.5 is less than g of 5, then g of 2.5 is not a maximum, because there's a y value that's bigger. For the last one, if g of 1 is less than g of 5, which is less than g of 2.5, that's still not enough for us to say that g of 2.5 is the maximum, because we could have something happening where the maximum is really at g of 3. So for example, our graph could look like this, where here's 1, here's 5, so here would be 2.5, and our graph might look something like where the maximum is not at 5, 1, or 2.5, but instead somewhere over here. So we know this isn't true. Similarly, to cancel out these other two, where we say g prime of 1 is less than 0, that means the slope at 1 is less than 0, and g prime of 3 is greater than 0. Well, that means we'd have some sort of a picture possibly going like this, where here's 1 and here's 3. Well, g prime of 1 is less than 0 means we're going to be decreasing. And then g prime of 3 is greater than 0 means we're going to be increasing at that point. So our graph could do something like, let's make that prettier, something like this, where we go up right there. But then 2.5 is not a maximum at all. So we can go ahead and say that this is not a solution. Saying that g prime of 1 is greater than 0 means our slope is increasing when x equals 1. So here's 1, let's say here's 3. So if our slope's increasing and then g prime of 3 is less than 0, means our slope's decreasing at 3, well, I could reach my maximum right here at, say, 1.5, and then just decrease all the way down. So here at, like, say, 2.5, I don't actually hit my maximum. My maximum's up here. So this also isn't a solution. So the things we need are, to be a critical point, we need our first derivative to equal 0. That's what you have to be any max or minimum ever. And to ensure that we are a maximum rather than a minimum or some other odd behavior is that we need to be concave down, which means our second derivative is less than 0. So we call this the second derivative test. So the things we need are only this term and this term. Okay, so for this first problem, we're told that the graph below is the graph of f prime of x, which means we're a derivative. So based on this graph, the function y equals f of x is increasing on what intervals? So we need to find where it's increasing. So if our function f of x is increasing, it means our slope is positive, right? This tells us that slope is positive. So if we know our slope's positive, well, we know that the y values of our f prime of x function equal our slope. So what we're doing is we're going to look up here at this graph that we're given, that represents f prime of x, and determine where that is positive. So if we look, we're positive everywhere between, I'll use a different color to highlight this, from here, right? All these values in here are positive, and everything after this value here is going to be positive. So those, if we want to write those as intervals, that's going to be from -1 to 1, because here we're at -1 where we cross, and here we're at 1 where we cross, and everywhere in between there we're positive. And from 4 on to infinity. And we're going to say these are both in parentheses instead of brackets, because when x actually equals -1 or x actually equals 1 or 4, the f prime of x value is 0, which means our slope is not positive, because to be positive we need to be greater than 0. So the correct answer would be -1 to 1 union 4 to infinity, which is going to be answer B right here. So for question 2 with this graph down here, The graph is of a twice differentiable function f is shown below. Which of the following is true? So we're asked to rank based on this value right here, essentially, this point right here of x equal to 6, the values of f of 6, f prime of 6, and f double prime of 6. So the first thing to note is that f of 6, we can just look at our graph to tell. It's going to be right up here, and it's going to be at y equals 6. So f of 6 equals 6. The next thing to note is that f prime of 6 is the first derivative. So it's going to tell us about the slope of our function. So the slope of our function when x equals 6, so what we can imagine doing is drawing a tangent line right there, and the slope of that line, since it's horizontal, is going to equal 0. Then for f double prime of 6, so f double prime is the second derivative, so it's going to tell us about concavity. So if we look here at our graph, we can notice that we are concave down. So if we're concave down, that means that f double prime of 6 is less than 0. It's going to be some negative value. We don't know what it is, but we can tell that it's definitely less than 0. So that means our lowest value would be f double prime of 6, followed by f prime of 6, followed by f of 6. So the correct answer is C. F double prime of 6 is less than f prime of 6, less than f of 6.